So this is our official proof of the product rule, and our goal is to get from here to here. And we're going to do this proof like we do most of our proofs. We're going to start on one side, the left side, and we're going to get it to look like the right side using valid math. And it would make a whole lot of sense that the place to start is with the limit definition for derivatives. In other words, I'm going to take the limit as h goes to 0 of my function f times g evaluated at x plus h, and subtract f times g evaluated at x, and all of that divided by h. So this is going to give me, literally, the derivative of the function f times g. And now, interestingly, I'm going to pull off a very clever trick. This trick could be taught as early as Algebra 1, but for some reason it is not often taught as early as Algebra 1. And the trick is very similar to the trick that we pull when we are adding or subtracting fractions. We have to get a common denominator, and so we take and we multiply that fraction by 1. You know that trick, right? Multiplying by 1. We're going to do the same thing here, except this time we're going to add 0. So the key move in this proof is to add nothing. But we're going to add nothing in a very special way. We're going to do it by adding and subtracting, actually by subtracting then adding, the same quantity, so that we have equality, but in a usable form. Here's why we need to do it. When we did constant multiple rule, when we did, constant multiple rule was a big one, we relied on the fact that we had a common factor of k that we could pull to the outside. Do you remember doing that proof? The problem here is I look in the numerator and I do not see any common factors. The factors here are f of x plus h and g of x plus h. The factors here are f of x and g of x, no common factors. So I'm going to introduce a common factor by subtracting f of x plus h times g of x, and then adding f of x plus h times g of x. Inserting that right into the middle right here. Algebraically, I can do that because I added nothing. I didn't change the value of this limit, but what I did was I made it so that I had a common factor of f of x plus h for these two terms, and I have a common factor of g of x for those two terms. And that's going to allow me to factor by grouping, so to speak.
How do you get a common factor for it? How did you...
Let me do one more step and I think you'll see it. Okay? And now the next part of the key move is to divide this very large fraction up into two fractions that have this common factor and that common factor separately. So here I have my first two terms, plus, over here, I have my next two terms. And the reason that I can do this is that division is this by h is the same as multiplying by 1 over h, and so I can simply distribute the 1 over h to these two terms, and distribute the 1 over h to those two terms.
So it's just a common factor. You just explain what a common factor is.
Pretty much, yes.
So I don't understand how you got the common factor.
Oh, in other words, what inspired me to do this? Yeah. Two answers. First of all, I saw somebody else do this kind of trick, and I said, hey, we could do this. I didn't invent the product rule nor this proof. So somebody else showed me this proof, and I think that was the first time I'd ever seen adding zero before. But then the second question is, how would you know in a future situation what kind of thing to do? Notice that I pulled one factor from this term and one factor from that term, so that when I have the two factors here, I automatically have a common factor for those two and a common factor for those two. So if you need to do that in the future, that's really how that trick is set up. Okay, is everybody comfortable with the algebra here? You wouldn't have necessarily thought to do that, but now that you've seen it, you see, okay, we're adding 0, and so we are adding, we're subtracting and adding one factor from here, one factor from here, so that when we now split this up here and here, then these two terms have that common factor, and these two terms have that common factor. Okay. Next step. Sum rule. We're going to split this up into two separate limits. That one. And that one. So notice that, unlike the proofs of our previous rules, not only does the product rule depend upon the product rule for limits, we'll see in a second, but also it's going to depend upon the sum rule for limits. So we have a sum rule happening right here. And now I think it's high time for those common factors to come out. Move this down just a bit. Pull this back up so you can see what we're doing. I'm going to factor out the f of x plus h. And I'm going to appeal to the product rule for limits here at the same time. I hope you'll forgive my doing two steps at once, but it's a little bit tedious to do every single step. So when I factor out the f of x plus h, then what's left behind is all of this right here. And now at this point you might be seeing the logic of this proof. And likewise, I'm going to factor out my common factor of g of x and use the product rule for limits right here as well. Are we good? Okay. And now, it's beauteous. As h goes to 0, f of x plus h collapses to f of x. And as h goes to 0, look at that quantity right there. What is that thing? We know that thing. That's the derivative of g of x. This one is possibly the weird one. Notice that h is going to 0 here, but x is not going to 0. H is not x, right? H is the little chain in x. And so as h goes to 0, g of x is just g of x. And then finally, we look at this quantity. What is that quantity right there? Of f. And we have arrived at f prime. Good show. Isn't that fun? So this is possibly the most complicated proof that we've done all year. And so we want to have a skeleton framework in our mind for it. That's why Earl wanted to have the ability to go back and take a look at it. And so here it is. The skeleton is, we set up the limit definition. We add 0. And it's a special 0 that we add so that we end up with common factors. as you practice this proof, that's going to be the hard one for you to remember. And once you do it like once or twice, you'll see the logic of it and it'll make sense. And then we grouped terms and did what came naturally. Once we had the terms grouped right here, then the rest of the proof was fairly clear. We had factoring and recognition of the various computation of the various terms. How are we doing? Yep, just right there. Instead of et cetera, I'll put in factoring, factor, and evaluate. Why do I have you learn proofs? Good question. Two reasons I have you learn proofs. One is that the learning of the proofs helps you to understand how the material interconnects together. Students very often understand math as a random, disconnected series of facts that you memorize. Oh, look at that. The square root of 9 is 3, just because. And when you do it like that, math becomes very hard to use. When you understand how math is interconnected, now math becomes easier to use because it gets smaller. You have only a few tools that you're using. And also because the tools relate to one another. So you can, if you can't figure out how to solve the problem this way, then you can go around the other side and figure out how to solve the problem that way. So that's the first and major thing that proves to for you. The second thing is it's a language game. You've heard me say it before, math is a language, right? And so as you learn to speak the language and understand what it means, then you become a master of that language. Language acquisition happens in stages. Think about how a baby learns whatever language you learned as a baby. English, Chinese, Korean. You learned it by spending almost 6 to 12 months of your life just listening to it. Just hearing what it sounds like. And then at some point you realized that the sounds were associated with actual things, right? That's the first stage of language, is nouns. And you say mama. And you're not sure what happened, but you see the smile on the face. And so you go, I must have done something right. Let me say that again. Ma, 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 ma. And that gets a good reaction. Then you finally realize that when your dad holds you and you say mama, he goes, no, dada. And then you start to learn there's a difference between mama and dada, right? Unless you're one of those kids. So the Keglet, who you see wandering around here, the Keglet spoke her first word when we were carrying her out of the house, and she saw a cat on the street, and she said, Kit Kat, 6 months old, Kit Kat. And she's loved words ever since. She just, she grabbed a hold of that language thing. We do the same thing in math. You guys are learning the math language largely by watching me do it, right? And also by speaking it yourself. So if you are uncomfortable with the math language, if it kind of freaks you out to do proofs and blah, 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 let me encourage you to not back away from it, but to jump in and start talking it as much as possible. If you want to learn French, the best way to do it is to plop yourself in Paris, $20, and try to figure out what's going on. So that you can get it.
I wouldn't recommend that too much because they can be pretty angry.
Especially
foreigners.
Okay, the French are snooty about it, but the way that they're snooty is they refuse to speak English to you. That's
That is true.
fabulous. I found it much harder to be in the Czech Republic and learn Czech because they all wanted to talk English to me. If you're in a country like France where they all want to talk French, France, then it becomes a great way for you to have to learn the language. You're putting yourself in a situation where you just got to learn it. Because you don't want to ask for the bathroom and end up at the grocery store.
But there's no doubt.
Maybe. Will they let you use them if you ask in English? Probably not. And not if you're chewing gum either. Not if you're chewing gum. No.
I actually don't know.
What was your favorite word when you were like really little kid? Like that you really wanted to remember?
Some places
No.
charge.
No,
Never.
a lot of those memories kind of fade. I got 44 years worth of memories.
It's almost half a century.
Alright. Oh!
So,
I don't think
In fact, I get to pull the last millennium card with people.
So do I.
Were you born in 99?
98.
yeah.
Wait, what? The last millennium?
Yeah.
Wait,
Like, I was born in the last millennium.
Oh, I think we can all do that.
Yeah.
Okay, you're all still there? Alright.
It's a weird film.
Oh, Reagan's not.
Reagan was born in 2000?
Yeah, Reagan was the youngest.
Alright.
She's not here.
Alright, so,
Oh, she's not here.
this is where you move from board. This is where you move from being mechanical calculus students to being smart calculus students. Because when a problem presents involving a product, you often have two options. Consider this one. I can do product rule on this thing. Or I can algebraically simplify inside first and then take the derivative of the result. Which one is easier here?
Depends apparently.
It depends, apparently, on how comfortable you feel with multiplying it out, right? He feels very comfortable multiplying it out, and therefore, algebra first is his best choice, because now you can take derivatives term at a time, boom, done. See? Easy. No product rule required. Now, we have confidence that if I had used product rule, I would get the same answer, right? Right? So we're good with that. But we want to understand that it is not necessary for me to use product rule first just because I have a product. Maybe I could simplify it. Does that make sense?
Wait, so you're saying, oh, so you're saying if there's a product, you could maybe simplify it, then you would have to do the product rule?
There you go. Right. Same kind of thing happens here. Do I want to use the product rule here? No, I do not. Look how easy that is to simplify. 4x squared minus x cubed, da-da-da. Ta-da. Easy peasy. But life throws us ambiguous situations. Did I mess up?
No.
Okay. Life throws us ambiguous situations. Do I want to multiply this out or use product rule? It kind of depends upon how comfortable you feel with multiplying it out versus using product rule. Yes?
What if you're both so iffy on both that you have no idea what to do?
Then you need more practice. And that's a real thing. Notice that the student often walks into this class with the assumption that what I'm supposed to do is to do the homework problems and I'm good. Well, actually, no. The real purpose of the homework is for you to master that material, right? So if you get to the end of that homework assignment, you say, I don't know what I'm doing, then you really should go back to easy problems and iterate on them until you've got it cold.
Is there any way to make this very fast and efficient, or will it have to be a long process? Because I know how to do it, and I can do it in a long process, but I'm just wondering if there's like a more efficient way.
Let's find out by counting steps. This side of the room, Jackson, and to your left. All of you multiply this out
Man, I'm already decided.
and take the derivative of it. Count steps. Everybody on this side of the room, Will and to your right. Use the product rule and simplify your answer. Go. We gotta make it easy, so you gotta simplify your answer.
Like step, middle step, middle step.
Yeah, each step that you have to take. We know already your first step is going to be the product rule. You people over here, right?
If you could skip steps in your head.
You're allowed to skip steps for polynomials. That's the only thing you're allowed to skip steps. I'm going to do the appropriate version for your side.
Yes.
I'm out of room, but does everybody understand I'm using product rule here?
Yes.
So? And now the simplification turns out to be the pain in the next step on the side, right? So we end up with x to the fourth plus 2x squared minus x squared is plus x squared minus 2 plus 2x cubed minus 2x squared plus 2x equals, and now I have to go through and collect like terms here.
Wait,
Okay,
Oh,
so ours is actually,
yeah.
I did both.
You did those.
I started that.
Good for you, by the way. Yes,
No. Why is
Skip this because I didn't see that option.
Oh, I just had to. That's just
Oh, it is 2x minus
Yeah.
1. Thank you.
Yeah.
That's the other thing that you want to watch for, and that is the possibility of dumb mistakes. We don't like procedures that encourage dumb mistakes, right?
These encourage dumb mistakes. All of that.
Yeah.
Oh, yeah.
Multiplying
Yeah.
by There's one problem last night, it's like, headaches and six.
Okay. And so now I go through and collect terms. Hey, speaking of procedures that help eliminate dumb mistakes, watch what I do just to kind of help out with the collecting of like terms. I go through and I identify the like terms with different squigglies. And what that does for me is it allows me to focus just on the question, what are my like terms?
I just crossed it out as I crossed it.
You can do that too. But what I'm doing by breaking it up into identifying and then combining is somehow I'm making those processes discrete so that I make fewer dumb mistakes.
Mr. Cable, x cubed, the second x cubed would be
D
2
to
x
the
cubed.
x cubed. Yes, you're right. So speaking of dumb mistakes, I find that when I am the least bit sleepy, those dumb mistakes get much more frequent. Do you find that to be the case?
Less. Did you say
When I'm more
less?
sleepy?
Oh, when you're more.
When I'm the least bit sleepy, yeah.
No wonder I made mistakes.
All right, now on this side of the room, let's see if I can do this correctly. We have the derivative of x to the fourth, distribute minus x cubed plus x squared
Yes.
Plus 2x squared
plus 2x squared
minus 2x
minus 2x
plus
plus 2. And we have a little bit of combining of terms to do right here. So that's going to give me the derivative. Right, we still have to do the derivative, but we notice that the derivative is relatively easy to do. We can actually go term at a time. 4x cubed minus 3x squared plus 6x minus 2. We have a win. So how would you rate these? How many do you like the one in black and blue?
Oh,
Wait, no.
How many do you like the one in red? Yeah. So now that we have some experience with it, you can see that considering algebra first is often a winner. However, Kyle, you need to look ahead. So,
Where's an example of where the calculus is better?
sometimes it's absolutely necessary.
I have a question. Do you ever have to do like chains of derivatives? Like the derivative of the derivative of the derivative of f of x?
We're getting there, but don't panic
No,
yet.
well,
Yeah.
you just keep taking the derivative or something
Until you get to this.
until you get an answer.
You need to be lady.
Okay, suppose I have this derivative right here.
Yeah.
Look ahead just a little bit. If I do the algebra first, I'm going to end up with two different functions that are going to require product rule, right? So I have to do two product rules instead of one. Maybe not a good idea. If I do the calculus first, then I only have to do one product rule. And added bonus. Nope, wrong. Okay. The added bonus is, remember this derivative from yesterday? Nope. Wow. This derivative is 1, so I get root x plus the absolute value of x. I may not have to simplify. Depending upon the situation here, if I am not called upon to simplify, once I've got my derivative, I can just leave it. Really and truly. Going back to our question here, let's reassess. Suppose I didn't have to do any simplifying, but I could just stop right at this point. Does that change the way that we feel about the calculus first? It kind of does, right? So the answer also depends upon context. We have to be sensitive to our context. So that if I do not need to simplify, that nudges me towards the calculus first. If I need a simplified answer for whatever reason, maybe I want to do the algebra first. So this is an ambiguous situation, which often happens when you're an adult. Which one do I choose? And the answer is, look ahead a little bit. And if you're not sure, try one. And if it seems like it's a real mess, try the other one.
That was called Follow Your Heart.
Follow your heart. You know, that's Disney movies.
Follow your heart.
Yeah, Disney movies, you follow your heart and it's never wrong.
Follow your heart for 3 twisted.
Because our hearts are so good, right? The last thing I want to consider is this question right here.
John Smith.
Could we extend the product rule? And if we did, would it be a formula worth knowing? If we were to extend the product rule, how do you think we might go about it? What do you mean by distributing? Distributing is a thing that happens with multiplication over addition.
Well, I just like, you would have to like, take f of x times g prime and f of x h prime, and g of x prime.
Okay, you're guessing at an answer.
Huh?
You're guessing at an answer.
Yeah, I thought we could do that.
No, I want to guess at a method here to get us there.
So I'm guessing you let another function be the product to these functions, and then you can use the product rule.
R of x equals g of x.
Or how about we just associate them?
Yeah,
We can use the associative property and use this as fg times the derivative of h plus h times the derivative of fg. And Earl, that gets us what we wanted, kind of like where you were going, but without any guesswork.
So then you just keep going. Oh, then you just keep going.
Yeah, that's right. And so that's not so bad. And furthermore, when we are done, it turns out we really like the result. It's fg prime plus g f prime. But don't forget your parentheses because we're multiplying h times all of that, right? And now here comes your distributing that you were hoping for. And that gets me hfg prime and hg f prime. Now, this doesn't look so wonderful, but let me rearrange the terms here. 1, 2, 3. 1, 2, 3, and write them in order. And watch what wonderful thing happens. Term number 1 is f prime g h. Term number 2 is f g prime h. And term number 3 is f g h prime. You see the pattern now? You see it? The product of all three, f prime, g prime, h prime. Just like that. Isn't that nice? So that's actually really useful. So for example, if I needed the derivative of x plus 1 times x plus 2 times x minus 4, then instead of multiplying out algebra first, instead of doing a complicated product something or another, I can just do f prime times g times h plus f, bless you, times g prime times h plus f g h prime. And then I can simplify that if I really need to, but I'm done in one step with the calculus model. Yes?
Will that work with more than 3 factors?
You can extend that out as much as you need. Now to prove that, we would need to do some kind of proof technique that allows extending, and that proof technique is called induction, which you will only try. Okay? Yes, sir. Ah, yes, so he had a homework question, and we are out of time, so what I'm going to do is, if you'll tell us that question now, I can do a quick review on it.
On question 37, I had worked out the derivative, but I was wondering how then to find the perpendicular angle to it.
Okay, were you here for the discussion of normal lines?
Yes,
Okay, that's it. It's asking for the normal line.
I know, but I don't know how, I personally don't know how to find the perpendicular to x squared. X squared.
Ah, you don't actually need to. So the curve, what was the curve?
The curve was x cubed minus 3x plus 1.
Okay, and was there a point involved?
2, 3.
Okay. So we compute dy dx, and dy dx gives us the slope of the tangent line at any point, right? And in particular, at the point x equals 2, dy dx is equal to 12 minus 3 is 9. Therefore, I'm going to notate this as dy dx perpendicular at the point x equals 2 is negative 1/9. And that's it.